Hello, my name is Eduardo and today I'm going to present the work entitled Identifiability of Dynamic Networks from Structure. In this talk, we look at the problem of determining identifiability of a network looking at specific structures from which identifiability results are available. Here is the outline of this talk. First, we will present the objectives of our study, dynamic networks. Then, we briefly recall and discuss the concept of generic identifiability. We then present the problem and some results that can be used as a divide and conquer strategy to determine generic identifiability. We also study two classes of networks where parallel paths are present, which are parallel networks and feed-forward networks. Finally, at the end of this talk, I present the conclusions we draw from this work. In this work, we consider a dynamic network as can be seen in this graph. We have node signals represented by W in the network. Between some node signals there are modules which are represented by discrete time LTI systems. Each node may be subjected to a no input signal R. The modules are collected in the network matrix G. Matrix B selects which nodes are recited, while matrix C selects which nodes are measured, to form the output of the network. Our objective is to determine which modules are identifiable from input-output data. We adopt the concept of generic identifiability from Basanella, Gervais, and Hendricks in CDC 2019. Generic identifiability is the ability to uniquely recover almost all network matrices G compatible with the topology of the network from the input-output representation T. Generic identifiability is related to the question of which nodes need to be assigned and which nodes need to be measured. A key result is the necessary condition that asserts that for any network, every node must be either assigned or measured. We adopt from our work present earlier at the session conference the concept of excitation and measurement pattern, EMP for short, of a network. An EMP is a combination of the set of excited nodes and measured nodes. Valid EMPs are EMPs that guarantee generic identifiability. We are interested in minimum EMPs, which are those valid EMPs with smallest cardinality of a network. The smallest cardinality that any minimum EMP can have is the number of nodes in the network. By characterizing the minimum EMP of a network, we determine all valid EMPs of a network. In this work, we are interested in determining the minimum EMPs for some structures of networks. More precisely, in this work, we tackle two problems. The first one is to determine conditions for generic identifiability when some results are available for specific structures within the network. As it can be seen in the top right corner, a network is divided into two subnetworks, each of which with a specific structure. Now, if we know a valid EMP for each subnetwork, we can apply it and then determine which additional conditions guarantee generic identifiability for the whole network. This problem can allow us to devise a divide and conquer strategy and to combine no identifiability results. A second problem is to determine necessary and sufficient conditions for generic identifiability of a dynamic network with parallel paths. We can see in the bottom right graph that there are some parallel paths in the network. For example, W1 is directly connected to W4, but there is also another path from W1 to W4 through W3. Our objective is to determine which conditions characterize minimum EMPs for these networks. Let us focus now in the first problem. We are going to assume that the two structures G1 and G2 are subjected to valid EMPs. We assume that there is no feedback between the two structures. That is, we assume that there are only edges linking G1 to G2, but no edges are allowed from G2 to G1. Then the red edge in the top right graph is not allowed in our setup. We also assume that there are no shared nodes in the two subnetworks. We introduce the definition of critical rank of a matrix A, denoted as key A, as being equal to L if every subset of L columns from matrix A are linearly independent. Here an example, where the first and third columns are linear independent. Therefore, the maximum pair of linear independent columns is equal to 1. Now, we are in position to tackle problem 1. We can partition the network matrix as following, and we obtain the input-output representation as described by the equations. Since a valid EMP has been applied to the first subnetwork, we can recover the network matrix G1 and G2 from the input-output model. Now, the only remaining unknown is G21, which can be only recovered from the bottom left part of the input-output matrix. In the graph, this is represented by the green edges. All the rest is known from the valid EMPs. We need to recover then G21 from C2, G21, B1. In other words, our problem is equivalent to determine which nodes need to be assigned at the first subnetwork G1 and which nodes need to be measured at the second subnetwork G2. Identifiability of G21 also depends on the topology of G21, that is, how G1 is connected to G2. The graph in the right represents the network divided into two subnetworks. The first result of this work is a theorem that states a number of conditions depending on the structure of interconnections between the two subnetworks. G21 is generically identifiable only if the number of the inputs in G1 multiplied the outputs from G2 is larger or equal than the unknowns in G21. If G1 is fully connected to G2, then G21 can be recovered if only if we assign all nodes in G1 and measure all nodes in G2. If only a particular node in G1 is connected to all nodes in G2, as we see for node 2 in the graph, then we recover G21 if and only if all nodes in G2 are measured and the corresponding row of G1 beyond is non-zero. The convex case, where all nodes of G1 is connected to only a node in G2, we recover G21 if and only if all nodes in G1 are assigned and the corresponding column of C2, T2 is non-zero. Finally, in the situation where G21 is composed of better disjunct paths, like in this graph, where a node in G1 is connected to at most one node in G2 and vice versa, then we must obey item A and a sufficient condition that depends on the critical rank of T1 B1 transposing and C2 T2. Now, let's tackle problem 2 of parallel networks. We have started our analysis with the network that we have called parallel network displayed here on the right. For this topology, we have derived necessary and sufficient conditions for generic identifiability. The first condition is that all sources need to be assigned. A source is a node with no incoming edges like W1. All sinks must be measured. A sink is a node with no outgoing edges like W5. Every node needs to be either assigned or measured. That is valid for any network. Finally, we need to assign and measure all nodes that are neither a source nor a sink, with exception of one. For example, we can relax the condition of assigning and measuring one node from W2 to W4 in this graph. We will call internal nodes those nodes that are neither a source nor a sink. A minimum EMP for this network has cardinality n-3. Another class of network with parallel path we consider is a feed-forward network. This class can be defined as every node being connected to all nodes ahead of it, assuming that the network has been labeled sequentially. We have derived necessary and sufficient conditions for generic identifiability of feed-forward networks. All sources need to be assigned and all sinks must be measured. Now, similarly to the parallel network, every internal node needs to be both assigned and measured. This is rather a strong condition, since these requirements are known to fulfill identifiability of any network. In this case, a minimum EMP has cardinality equal to n-2. With the objective of relaxing these strong conditions for internal nodes, We have developed conditions for when it's possible to relax the excitement and measurement requirements for an internal node of a feed-forward network. We have then a more general class of networks where some modules do not exist in the network. Then we can relax the excitation of our internal node L if and only if each row of the selection of rows and columns from matrix G has a node 0. This selection is done by subset D, which depends on the node L and is defined below. Let's analyze an example of the network depicted in the right side. Consider that we are interested in determining whether we need to excite node 3. We look at the rows 4 to 6 and columns 1 to 3 of matrix G. Now inspect each row of this matrix to see whether there is a node 0. In this case, we do not need to excite node 3 since the second column of this matrix is 0. If there was an edge connecting node 2 to 4 or 6, for instance, then node 3 would need to be excited. We have a similar result for when an internal node should be relaxed for measurement. In this case, the condition is based on the columns of the matrix G. Now, in this slightly different example, G42 is present and we would need to excite node 3. But now we are interested in node 4. We then look at the network matrix and verify whether there is a node 0 in each column. As there are no zeros in each column of this matrix, we need not measure node 4. However, in a similar way to the last example, if G51 or G53 were present in the network, we would need to measure node 4. These results presented so far can be used along with the results presented at the beginning of this presentation to adopt a divide and conquer strategy and determine generic identifiability. Consider the network depicted in the right side. In this example, we can recognize two well-defined structures. The first structure represents a feed-forward network, for which there is only one minimal EMP characterized by exciting nodes 1 and 2 and measure nodes 2 and 3. The second part of the network represents a subnetwork with cycle topology, and we know from Bezonella CDC 2019 that a minimal EMP has cardinality 4. This means that we must excite and measure a node within the cycle, while all other nodes can be either excited or measured. For this subnetwork, there is a total of 12 minimal EMPs. Using these minimal EMPs, we need to verify if the vertex disjoint D21 obeys the conditions in Theorem 1 item E. Applying these results, we observe that all combinations of minimal EMPs can render the whole network generically identifiable. It is not our aim to obtain a minimal EMP for the composite network, but using this strategy, we can obtain the minimum cardinality with respect to each part of the network. Furthermore, all 76 combinations of valid EMPs satisfy the conditions of the theorem, and G21 can be generically identifiable. In this example, we have thus combined easy-to-use formulas for each part of the network, and all combination of these formulas result in generic identifiability for the composite network. In this work, we have tackled the problem of identifiability from the perspective of the structure composing a network. We have shown that knowledge of identifiability conditions for specific structures can be used in the process of determining generic identifiability. We have presented conditions in Theorem 1 for this problem, which depends on the topology of the interconnection of the two subnetworks and on the excitations in G1 and measurement from G2. In the second part of the work, we have derived necessary and sufficient conditions for parallel and feed-forward networks, showing that most nodes need to be excited and measured. Finally, we have presented conditions on Theorem 4 to know whether an internal node can be relaxed from being excited or being measured for a more general case of feed-forward networks. We are currently extending the results presented in this talk to the case where feedback among the structures is allowed. We are also looking at necessary conditions for the case where the internet connection G21 is vertex disjoint. for which we presented sufficient conditions in Theorem 1. With this conclusion, I close my presentation here. Thank you for your attention.